Hi guys, AP Chemistry. This is Chapter 11. This is actually Section 3. This is the other half of the first video that I felt was a little too long, so this is the second video. And this one is going to be Section 3 of Chapter 11. No math, all concept. This is going to be factors affecting solubility. And we are going to go over structure effects, temperature effects, and pressure effects. Okay, so the first one we're going to discuss is structure. Please remember from the last video, there's a lot more to going into the dissolvability of an ionic salt than just throwing it in water. You have to separate the intramolecular electrostatic force between the cation and the anion endothermically. Separate them. You have to separate the intermolecular force between water molecules. Then the separated cation and anion have to get in between those separated water molecules. And the closer they get to those water molecules, the tighter the fit, the more exothermic energy is released. So you got two endos and an exo. And polar versus polar, polar versus nonpolar, like dissolves like. A polar solute and a polar solvent will be approximately a 0 enthalpy of solution formation. A nonpolar solute and a nonpolar solvent will be approximately 0 enthalpy of solution formation also. It's when you're trying to mix a polar with a non that it's not going to happen. So that was the previous video in a nutshell. And this one talks about structure or polarity of the structure, nonpolar versus polar. Hydrophobic is water fearing. Hydrophilic is water loving. So a couple of definitions. You know already phobic means fear of, so hydrophobic means fear of water. And again, just like the previous video, like dissolves like, I have two vitamin structures here. Notice vitamins are really organic compounds. Carbons, hydrogens, oxygens floating all over the place. Vitamin A is on the left and vitamin C is on the right. Vitamin A is a non-polar fat soluble. Look at all those carbon-hydrogen bonds. You know that carbon-hydrogens bonds are non-polar. And even though it has that little bitty polar oxygen-hydrogen, the entire molecule, which is pretty big, this is vitamin A, is pretty big. It is a non-polar molecule and fat soluble. That means this vitamin A gets absorbed into the fat of the body. Opposed to vitamin C, which is first off slightly smaller. Secondly, a lot of polar bonds all circled for you. So vitamin C is a very polar molecule and it's water soluble, obviously. Polar versus polar water. This one's going to dissolve in water. Vitamin A is not. Vitamin A is nonpolar. Fat is nonpolar. Fat is nothing more than a bunch of hydrocarbons also. Polyunsaturated, etc. So fat is a bunch of nonpolar molecules also. So vitamin A will dissolve in fat because it's nonpolar and a nonpolar, whereas vitamin C is going to dissolve in water because it's a polar versus the polar. That's why you need to take a daily dose of vitamin C, because it gets dissolved in water, run through the body, and you basically pee it out. Whereas vitamin A gets dissolved in the fat of the body, and of course you don't pee out fat, although that would be awesome. But it doesn't happen. So vitamin A gets retained in the body. Vitamin C does not, because it goes out with your pee, your urine. A couple of other fat-soluble vitamins are A, D, E, and K. A couple of other water-soluble vitamins are the rest. So like dissolves like. Polar dissolves polar. Non-polar dissolves non-polar. A non-polar will not dissolve in a polar. Second factor that affects solubility, temperature. The dissolving will occur more rapidly, not more, but more rapidly at higher temperatures. The solubility of a solid might increase or decrease with temperature. So solids, salts, ionic compounds, are dependent on the type of compound to determine if they will dissolve more or less in high temperatures. The solubility of a solid might increase or decrease with the rise in temperature. Gases are straight up. The solubility of a gas will decrease with higher temperatures. Gases are soluble in water. Oxygen gas is dissolved in any lake, stream, ocean. That's how fish breathe. Fish need oxygen to breathe. That oxygen is dissolved in water. Fish kill, Google it if you've never heard the term. If the lake gets warmer, less oxygen gas is dissolved in that lake. More of the oxygen gas is coming out of the water and escaping to the air. If you have less oxygen in the water, dissolved in the water, then the fish can't breathe because the fish can't get the oxygen and the fish die. That's what's called a fish kill, especially with lakes that are suddenly increasing in temperature. This is a solubility map or solubility graph of a variety of solids. This is a map that shows these solids at a variety of temperatures also. A couple of things to note. It is traditionally this graph has temperature on the x-axis and the solubility of the solid on the y, and the solubility of the solid is listed as grams of solid solute for every 100 mils of water, because of course water is our most popular solvent. The vast majority of solids will increase solubility with an increased temperature. Only 2 of them are depicted as not, and that is the sodium sulfate and the cerium sulfate. They actually go down in solubility with an increase in temperature, but the others go up. Notice sugar goes up substantially. Look at the potassium nitrate. Its solubility increases tremendously. And again, with a higher temperature, it doesn't necessarily mean more dissolves. It means it dissolves more rapidly than at lower temperatures. So again, solids vary with an increase of temperature. Gases do not. They all go down. The solubility of a gas will decrease with an increase in temperature. Pressure? Think soda pop bottles. Henry's law, the amount of a gas dissolved in a solution is directly proportional to the pressure of the gas above the solution. So the higher the pressure of the gas above the solution, the more gas dissolved in the solution. That's why your soda pops are bottled at high pressures, because of course the higher the pressure, the more carbonation in the soda, and the minute you unscrew that cap, bam, that pressure comes down to 1 atmosphere, and a lot of that carbon dioxide comes out of the solution. That's why you get the bubbles in your soda pop. That's why your soda pops go flat over time, because all the CO2 is coming out of the solution and escaping. There's a calculation, just know it exists, and it verifies the definition. The amount of gas dissolved is directly proportional to the pressure of the gas above the solution. Concentration, pressure, and a constant. It's just a relationship, so make sure you understand the relationship. And again, soda pop bottles and cans. All right, nice and short and sweet.